Okay, so welcome to Chapter 7. This is Lecture 6, Lecture 5, which teaches Chapter 7. And Chapter 7 has problem set 8 in it, so you're going to be doing problem set 8 in Chapter 7 after you watch this Lecture 5. Okay, so today we'll be going over derived rules, and we'll find out what that is. So far, you'll remember we have 4 rules of derivation, direct derivation. We have modus ponens, modus tollens, double negation introduction, and double negation elimination. So that's what all these are. Modus ponens, modus tollens, double negation introduction, and double negation elimination. We also have 3 types of derivations. We have our direct derivations, our conditional derivations, and indirect derivations, right? So that's different ways of doing derivations, whereas these are different rules of direct derivation, all of these, right? Again, the direct derivation is where we show something directly in the proof, just follows from the premises. The conditional derivation is where you want to show a if-then claim, so you assume the left side of the if, and then you show the right side of the if comes afterwards. And the indirect derivation is where you assume something, you show that it produces a contradiction, or a contradiction comes later after it. And so the thing you assumed can't be true, so you get the negation of the thing you assumed. But if we want, we can add new rules of direct derivation as much as we want. And these will make our lives much easier as we go on. So let's remember that all our derivations could apply to any inserted variables, right? So when we use like a letter like P or Q, if you changed all the P's in an argument to R's and you changed all the Q's in an argument to S, everything would still work, right? They're interchangeable. They're variables, basically. And so that means if we show that something follows with one set of variables of letters, we know it will follow no matter what letters you substitute in, as long as, like, every time that you had a P, for example, you replace it with an R, and every time you had a Q, you replace it with an S, so you're consistent. But if you change one set of variables for another, we know it will always follow in our system, right? And so if we can prove an argument is valid, we can then give it a name and deploy it in other proofs, because we know, if we change all the letters, it could still just work just as well. So if we prove some argument is valid, we give it a name, and then we know that we want to use that argument that we just proved in a different proof. We can cite it, basically. We can say, oh, well, I've already proven that this is valid, so I can just make this move for free. I don't need to show you the steps. So this would let us skip in other proofs all the steps that we needed to show that an argument is valid. So you show an argument is valid once, you give it a name, and then in other proofs, if you want to use the argument you already proved, you can just say, oh, well, I already proved this, so we can use it now. Again, our derivations and derivation rules are not case specific. They're always going to be valid for whatever set of variables you put in, or formulas or assertions. And so, for example, if P, then Q, and P, if those are your premises, you can always show Q, right? No matter what you substitute for P and Q, because, that's modus ponens. It applies to everything. So yeah, if we can show that something follows from a set of premises, we know it always follows from those premises in our system, and we can give that a name, deploy it as a new rule of direct derivation, or inference if you want, but we'll say a new rule of direct derivation. Yeah, again, this lets us skip steps. Man, it seems like I repeated some of the information in this, but it's good to actually have this example here. So whatever, we'll keep that. I went over it twice. Maybe that's helpful. I don't know. Okay. So I'll give you an example of how a derived rule might make our lives easier. So here's a proof using no derived rules, just the rules we already know. You can see it's 15 lines long. It's unwieldy. It's got this nested nested proof in it of a conditional derivation. You assume P and you show R. We don't need to go over all the steps. The point is just look how long this is, and there's a nested derivation. But if we just incorporate one derived rule, which we're going to call hypothetical syllogism, then we can make the proof much nicer and easier for us. So you can see this is a proof of the same or a valid argument. If you go back and pause the video and compare it to what's here, you'll see it's the same. But you'll notice it's only 11 lines instead of 15. And there's no nested derivation. It's all just direct. There's no assuming or anything. And that's because you can see here I cited a derived rule. The D here is saying, oh, I'm citing a derived rule. And the HS is saying which one, because you give it a name. In this case, it's something called hypothetical syllogism, which you will soon learn what that is. Yeah. So, but you can see the point is just that, after I explain to you what a derived rule is and I show you some examples, this will make more sense. But the point is just if we have a derived rule, we can take a big long proof like this 15-line proof with a whole nested derivation in it, and we can turn it into this shorter 11-line proof without any nested derivations. So let's just skip a few steps. Yeah, so it lets us save, actually, it lets us save 4 whole lines. Excuse my counting. And it lets us avoid any nested derivations, which are always ugly and complicated, right? So I'll show you how to produce these, and I'll tell you what they are named. And I'll explain to you how to follow along in Carnap. Yeah, just as you're doing it, you have to make sure you're logged in, because if you can produce these derived rules, you can save them for your future use, and that will be quite helpful for you. Okay, so now I'm going to switch to showing you some stuff on Carnap for a while. All right, so for our derived rules, we're going to do things just a slightly bit different. Instead of doing examples of exactly the kind of thing in the problem set, I'm going to show you how to do the derived rules, because in our chapter 7 today, or I'm sorry, yes, chapter 7 today, yeah, the problem set there is going to ask you to apply the derived rules. So I'm going to show you how to make the derived rules, how to save them. I will do one example where we apply it, and then you will do the rest in your problem sets. So we're going to go to our carnap.io like normal to do our stuff in Carnap. And then make sure you're logged in. That's absolutely vital. So you can see, my name is there. And that, shows I'm logged in. Make sure you're logged in, because you're going to need to save rules to your account today. Go to the book, or if you want, you can go to your, whatever, the front page of the course, and you can click on problem set 8, because that's where we'll be going. But we'll go to the book, click on book, and then you're going to want to open 2 tabs here. So first, right click on index of rules and open it in a new tab, and then click on chapter 8. I'm sorry, chapter 7. Oops. And you'll see derived rules, and there's a quote here from Spinoza, who actually is a philosopher who I do my research on. Your instructors do research on various things, and this is one of the guys I do my research on. But anyway, you can read that. You should read the whole chapter like normal. But you can see throughout the problem set 8 that's in chapter 7 is going to ask you to do a bunch of proofs that are made a lot easier by using derived rules. So in this case, it's greatly simplified by using hypothetical syllogism, which is one of the derived rules we're going to learn. So what I'm going to do is I'm going to show you how to prove these derived rules. For the example, in this case, we have hypothetical syllogism. And then I will use it in one of these just to show you the idea. But then you'll do all the other problems. So, okay. So let's look. What's the first derived rule we need? It's hypothetical syllogism, which looks like this. Now we know that the textbook uses Greek characters, but we can just use whatever. So I'm gonna work it out. I'm just gonna copy it for now, make our lives a bit easier. And then I'm gonna go over to my other tab here where I have my index of rules. You can see it lists all the rules that we have learned already: modus ponens, modus tollens, double negation, elimination, double negation, introduction. It lists all the others that we will learn eventually, not right away. But we'll go down to our index of derived rules. You need to do this yourself as well to be able to use them in the problem set. So how are we going to show them? Well, I know that we want to show this. Here, I'll zoom in so it's easier to see. So I copy and pasted it, but you know, whatever. We're going to substitute these for P's and Q's. Okay. So what is this saying? It's saying, well, if you have if P and Q, and if you have if Q then R, then you want to be able to show if P then R, right? But we need to make this look like a normal proof. So what I'm going to do is I'm going to make a show line. We want to show if P then R. And then under it, you indent like always. We'll put our premises, which are P arrow Q, call that a premise. Q arrow R, call that a premise. And then now we can delete this. I just have this here for keeping track reasons. But we'll get rid of that. And the system will know once we close everything that because we listed the premises and we listed what we were trying to show, it will be able to build up the valid argument in the no rule found thing here. It will eventually just show what we're trying to prove. Okay, but let's do this like a normal derivation. So we're trying to show if P then R. How do we show an arrow like this? Well, we assume the left side and we show the right side, right? So let's do that. Let's assume P. Well, conveniently, we can get Q by modus ponens on 2 and 4. You can see here. And then conveniently, we can get R from modus ponens on 5 and 3, because we have the left side here of this if then, right? And then you can see, well, after we assumed P, we were able to show R. So we can close this conditional derivation, because remember, we're trying to show a conditional, and we did what we had to on line 6. So now you can see it populates what we were trying to show. If you have if P then Q, and you have if Q then R, you can get if P then R, right? So now we'll save it. We're going to call it HS for hypothetical syllogism. We have to give it a name. If I were you, I would name all the derived rules exactly what I'm going to name them. If you want to give them a different name after you named it once, you have to prove it again and then resave the new name. So in this case, I'm going to call it HS for hypothetical syllogism is the name for it. Click OK. It's been saved. The page refreshes. And now we can use it in our problem sets. We have to refresh the page first so that the system knows that we have a new rule. But let's try to use it in this proof, right? Because if you look at all this, like there's a lot going on here. A lot of conditionals we're dealing with. But we can make it a lot shorter if we just use our new rule. So let's start our proof like normal. We are trying to show if U, then T, right? So now let's list all our premises. There's a lot of them. We have Q, then R as a premise. We have P, U implies S, which is a premise. Oops. And we have to fix the grammar here. There we go. And then our last premise is if S, then T. Okay. So how can we prove if U, then T? Well, first we'll assume U, because we want to be able to show that T can follow from it, right? All right. So what do we have here? Well, we have this if P then Q and if Q then R. Now, if we remember what our hypothetical syllogism is showing, it's showing here, I'll just put this in this space, this isn't part of the proof, but it's showing that if you have if P then Q and you have if Q then R, then you can get out of that if P then R, right? That's what hypothetical syllogism is showing. Well, conveniently, we have something that looks just like that. We have if P then Q and we have if Q then R. So we know that we can get if P then R by using hypothetical syllogism, which we just used, or we just derived and saved to our account. So we know that we can get if P then R. So let's put D for derived rule. All your derived rules, you have to use a D and then a dash and then whatever you named it. In this case, it's HS for hypothetical syllogism, right? And we did it using lines 2 and 3. And you can see the system is happy with that. You can see if I forgot the D and I just put HS for hypothetical syllogism, it would be really confused. It would say it doesn't know what rule I'm using or anything. But if I put a D with a little minus sign, it is perfectly satisfied. Okay. Well, now we have if P then R, and we have this line here, line 4, that says if we have if P then R, then we can also get if U then S, right? So from that, we can do modus ponens because we have the left side of this if then claim, right? So then we get if U then S by modus ponens on lines 7 and 4. Great. And then we can see, oh, we have a U already from our assumption. So we can get S. Yeah, so we can get S by modus ponens. So let's get S by modus ponens on 8 and 6. Which finally, from this premise here, if S then T, we can get T, which is exactly what we were looking for. So we can get T by modus ponens on 9, which has our S, and 5, which has our if S then T. So now we have T, which is fantastic, right? And we can produce our conditional statement we were trying to show, because after we assumed U, we got a T. So conditional derivation on line 10. There you go. So this is correct. This is part of the problem set. So you would hit submit. It'll be submitted as always. Yeah, but you can see like this is one way of applying direct derivations. So I'm going to show you the rest of these derived rules. I'm sorry, this is one way of using derived rules, not direct derivations. In fact, we use a conditional derivation, not a direct one. Okay, great. So what I will do now is I'm going to show you how to prove the other derived rules, and then I will let you guys figure out how to apply them in all of these. And if you look at the textbook, it'll tell you like what derived rule is useful when. Like this one says, oh, if you do these exercises, you'll find you benefit a lot from using the material conditional rules, which we'll prove together. And if you keep going down, it will say, oh, contrapositive rules are helpful here, or the dilemma rule is helpful here. etc., for all of these. So I'll show you how to prove the remaining rules, and then you guys can apply them. But do make sure you are also proving them and saving them to your account. And each time you prove one, you refresh the page. You can see my answer was gotten rid of, but if you already hit submit, then it's already counted as complete. So don't worry about that. Just move on to the next one. And you can always see which questions have been counted as submitted by looking at your homepage, the course's homepage. Okay, anyway, let's go back to proving some derived rules. Okay, so let's go ahead and prove the remaining derived rules from the chapter so that you can all do problem set 8 from chapter 7. And again, just keep an eye on in the chapter when you're doing the problem sets. Right above it, it'll tell you what rules might be useful for doing that problem. But as you can see on the right side of the screen, I've listed all the derived rules that we're going to prove. And I'll walk you through them, and I suggest using the same names that I've given them. Technically, you don't have to, as long as you always cite them using the name you actually gave them. But it'll make life easier if we all use the same names for rules. Okay, so the first rule we're trying to prove is what I've called material conditional consequent. The textbook just calls them the material conditional rules, but I call it consequent because, you know, from P, we're going to show that P is the consequent of any if-then claim. Okay, so what are we trying to prove here? Well, we're trying to show if Q, then P. And our premise is P. How do we do this? Well, you know, we're trying to show a conditional, so we're going to assume the left side and get the right side. Q by assumption. Oh, well, it turns out, you know, P is already a premise. So there you go. You get a conditional demonstration just like that, line 4. Then you see it pops up there. So I'm going to call it MCC for material conditional consequent. There you go. And then let's do the other material conditional rule. This one I've called MCNA for material conditional negation of the antecedent, because we're going to show if P then Q from the negation of the antecedent from the left side, negation of the left side. So let's do that. P then Q, if P then Q. Our premise is not P. All right. So how can we get Q? Well, we're trying to get a conditional, so we'll do another assumption. We will take P by assumption. And then we want to get Q, right? Well, conveniently, you'll see here we have these two contradictory things already, right? So let's show not Q. And remember, we can do this by showing that not Q leads to a contradiction. So let's assume not Q by assumption. Well, conveniently, we have these two lines which are still accessible because they're not from a closed earlier proof. They're just from an open proof still, and earlier in the whole derivation, the whole proof. So we have access to P and not P, lines 2 and 3. They contradict, so we can do indirect derivation on line 2 and 3. You can see it closes nicely. So we've shown not Q. So from that, we can get Q by double negation elimination, right? Because we can always remove two negations on line 4. And then we close everything. We did a conditional demonstration because we assumed P and we got Q on line 7. You can see it gives us the rule right there. All right. So you hit save. I did MC and A for material conditional negation of the antecedent. Hit OK. And then it saves a new rule. Okay, so let's do this one. Oh yeah, so this I called contrapositive 1, and this one I called contrapositive 2. So this is a O, not a 0, so keep that in mind. Contrapositive 1, contrapositive 2. All right, so what are we trying to do? We are trying to show not Q implies not P. And our premise is P arrow Q. Okay. Whoops, didn't indent. All right. So what are we doing here? Well, again, it's another conditional, so we'll assume the left side. And we want to get not P, right? Well, conveniently, we can get not P by modus tollens, because we have the negation of the right side of this statement, right? And we can do it with lines 3 and 2. See, that's nice. So again, we have another conditional derivation that we close on line 4. There you go. From P arrow Q, you can get not Q arrow not P. So we'll save that. I call that one contrapositive 1 with an O, not a 0, because 1, the word, starts with O. Saves the rule. The next one, we're just going to prove the other way. We're going to show P arrow Q, and our premise is, oh, I'm sorry, we're going to show Q arrow P, and our premise is not P arrow not Q. Okay. So again, we're going to assume Q because we're trying to show a conditional, right? So what can we do here? Because we want to get P. Well, we know not P. We could use double negation elimination on it, right? Oh, I forgot to say that's a premise. Okay. So not P, if we could get it, we could give us P, because we could do double negation elimination. So conveniently, with this Q that we've assumed, we can get not Q by double negation introduction, right? On line 3. And then from that, we can get not P, right? Because we have the negation of the right side of this statement by modus tollens on 4 and 2. See, it likes that. Everything is good. And then with this not P, well, we want to get P, right? So we will do double negation elimination on line 5. And just like that, we assumed Q, we got P. So conditional derivation on line 6. You can see it's happy. It puts in the rule there. So we're going to call that one contrapositive 2 with a T, because the first letter of 2 is T. Save the rule. Great. Okay. So the next one we're going to prove is dilemma. I put DIL for dilemma. So this one is kind of interesting. We're going to want to show Q, and we're going to use P implies Q as a premise, and not P implies Q as a premise. Okay. So where are we going to go from here? Because, you know, we can't just like assume P, because that will just give us if P then Q, right? It won't get us Q. We need a P from somewhere else or something. I don't know. But if we can, you know, we can always take the route of showing that the negation of Q leads to a contradiction, because then we get not Q, and if we have not Q, we can double negation eliminate for to get Q. So let's do that. Okay. So let's show not Q by assuming Q and getting a contradiction, right? So you can see we've opened a nested derivation here. Well, if we have not Q, we know we can get not P, right? By modus tollens. Modus tollens on 2 and 5. Right? Yeah. Okay, good. That's good. And then from that, we can get Q from modus ponens, because you see we have the left side. We have not P now. So we can get Q by modus ponens on 3 and 6. But you can see in this proof, there's a not q and a q. That's a contradiction. So assuming q leads to a contradiction, which means we'll get not q. So we'll say we're closing our indirect derivation. Remember, we wanted to show that this led to a contradiction. The contradicting lines are 5 and 7. So now we have access to this not q, right? And that's great because now we can get q by double negation elimination on line 4. And look at that, we wanted to show q, we did it. And since we were just trying to show this directly, it is a direct derivation on line 9. And look at that, there's the rule. So you'll save it. I call this one dil for dilemma, DIL. Hit OK, it's saved. And there you go. All right, and then we want to do CM. So this one has a nice Latin name. It's Consequentia mirabilis. And it's interesting. It's kind of funny looking, but it's true, it works. So we want to show P, and our premises are just not P implies P, right? Okay. Well, how are we going to get this? Well, we can show that assuming not P leads to a contradiction, which, I mean, it looks pretty obvious, right? If you assume not P, you're going to get P, so you'll have two contradicting things. So we're going to show not P by assuming not P, right? Oh, I forgot to write that this is a premise. There you go. All right. So with our not P, we can get P by modus ponens on lines 4 and 2. And look at that, there's a contradiction right there. So we can close our indirect proof and we can get access to not P. So indirect derivation on 4 and 5, because those are the lines that contradict. And then we can get P by double negation elimination, right, on line 3, because we have access to line 3 now. Well, we just wanted to show that we made P approve in the proof. We made P appear in the proof. So this is a direct derivation on line 7. And look, there's the rule right there. So we call this one CM for Consequentia mirabilis. Ah, I miswrote it. It needs to all be in capital letters. Okay. And then the last rule we'll be proving is really fun. EFQ stands for ex falso quod libet. Has a good Latin name. It means from falseness anything. So, or from falseness whatever, or from absurdity whatever, depending how you translate it. So let's do it. Sometimes in English, this one is called the principle of explosion, because the idea is if you have two contradicting things, you can prove anything. So you just explode the truth until whatever you want. But anyway, let's just do the proof. So we have not P as a premise, and we have P as a premise. Okay, well, conveniently, we can just do another double negation elimination here. So we want to show not Q. So we'll assume not Q. And oh boy, do we already have access to a contradiction, right? So we can close the indirect derivation because, again, we have access to these. They're not from a closed nested proof above this one. They're just from the main proof. So we can close an indirect derivation using lines 2 and 3, right? Look at that, it's happy. That means we now have access to not Q, which means we can get Q from a double negation elimination. I need to say where I got that. We can get Q from a double negation elimination on line 4. And then finally, we wanted just to show Q, and we showed Q, just made it appear in the same line. So it's a direct derivation on line 7. And look at that, we've proved it. So that one we're going to call EFQ for x falso quadlibet. There you go. So that's all the derivation rules, the derived rules that you'll need. Go back to, I suggest doing all this first, actually, so that they're all saved already. And then, I don't know, keeping this tab open that you have here. Open a new tab, go to the book, go back to chapter 7 on derived rules, and then work through all these problem sets using the derived rules. And again, I'll say the book tells you a little bit where the arguments will be useful or where the derived rules will be useful. So it tells you, you know, for these next two, 8.3 and 8.4, the material conditional rules will be really handy. And those are the ones that I called MCC and MCNA, right? Or you scroll down a bit, it will tell you, you know, for 8.8, consequentia mirabilis and some others will come in handy. So it gives you some warning about what to look for. This last one, it's going to give you a pretty significant hint about how to try to get 8.10. And it's going to combine a number of the derived rules. But just remember, you know, when you're citing a derived rule, like let's say, I mean, this isn't how it will look necessarily, because we always start with the show line, right? So let's say I was going to show S, and then, I don't know, I list all the premises. I'm not doing it here, but suppose I did. And then I wanted to use a derived rule. I would have to put, I don't know, whatever I was proving, and then the justification. Before you write all these abbreviations, you know, you have to put a D and a minus sign or a dash, and then list what you're saying. So it could be like dill somehow, you know, it could be D/MCNA, or it could be D/HS or something, right? So yeah, just remember to cite them properly so you don't run into problems. But yeah, so I will leave you guys to doing that. The chapter is really interesting. I suggest you read it. It gives you extra context for the rules, like how you can think about them. I didn't give that because I don't think it's super necessary. What's important is you can derive the rules like you did in your rule list over here. That's the most important thing. Yeah, you can see my complete one here. The most important thing is you prove them and you save them, and then you know how to apply them. But yeah, definitely read the chapter. The explanations of the concepts here might be helpful for you and everything. So, you know, keep at it. Keep trying until you get it. And there you go. That's how you get started in all this. So thank you for listening to Derived Rules. We're only doing chapter 7 today. Next week we'll be doing chapter 8, which is actually our last chapter before the midterm. So, you know, our next class, I should say, might not be a week from now, depending on when you're taking this course. But yeah, so next class we'll be doing chapter 8, which is the last chapter before the midterm. So, you know, keep doing your practice, keep attending the live sessions, bring in questions you have, and yeah, I'll see you next class. Thank you.